Okay, so the aim of the last video was to be able to understand how to sketch a locus which looks like this. So we want all the complex numbers z which satisfy this condition here. So the first way that we're going to think about this is geometrically. So as we normally do with geometry thinking, we're going to think about z minus 3 as the vector which starts at 3 and goes to z. So let's draw an Argand diagram and let's put on that complex number 3. So 3 just sits on the real axis, let's put it there. So we've got to work out where does z need to be in order to make sure that the vector that starts at 3 and goes to z has an argument of pi over 4. Well, if we draw a line which moves off, starts at 3 and moves off at an angle of pi over 4 like that, then that is going to be our locus of points. Let's try and convince ourselves that that works. Let's say that z is some complex number which is on this line that we've just drawn. Let's say z is there. Then what we're saying is that this complex number has an argument of pi over 4. Well, z minus 3 is this vector which starts at 3 and goes to z. But we've got to be a little bit careful because it's not actually a vector. What we really mean is z minus 3 will be the complex number which has position vector the same as this red vector there. So really what we mean by that is z minus 3 is a complex number which is a point which is out here, and those two red vectors are going to be the same as each other. The position vector of z minus 3 is that red vector. Well, we want the argument of that red vector to be pi over 4. Well, because those red vectors are the same as each other, and that angle is pi over 4, then that is true. So z could be there. You don't need to worry too much about why we have to move that why really we should move that red vector to the origin. You can kind of think about it as the argument of a vector is the angle that it makes with the positive real direction, like that. So that black line's our locus of points then. You might be wondering, why have I only drawn half the line and why have I not continued it? Well, let's imagine we did continue that line and that z could actually lie down here on this dotted part of the line. Well, the vector z minus 3 would be this vector which starts at 3 and goes to z. And we're saying what's the argument of that complex number which has that position vector? Well, the argument of that complex number would be the argument of this angle here, which is actually 3 pi over 4. Now, actually, the argument would be minus 3 pi over 4 because we've rotated in the negative direction. So you can see that we can't be down here on this line because that won't give us an argument of pi over 4. So in general, if you've got a locus which is the argument of z minus some other complex number, let's say z0 or z0 is equal to theta, then that's going to be what we call a half line, which starts at z0, let's label z0 on our diagram, and moves off at an angle of theta to the positive horizontal. So if you're drawing a dashed line for the positive horizontal to the right, then that angle there is going to be theta. Next, let's try and think about this problem algebraically. So we're actually going to look at a couple of different ways of thinking about this. So one way would be to use the fact that we know that the locus is going to be a line like that. And what we could do is we could say, well, I know the point that this line goes through. It goes through 3. Let's try and work out the gradient of this line. Well, if I label in the angle, which is pi over 4, and I draw in a right angle triangle on the line, so let's draw in a right angle triangle like that. Let's label this right angle triangle, that's the opposite side length, and that's the adjacent if we're doing trigonometry. Then we know that the gradient of this line is just the opposite side length divided by the adjacent side length. But opposite divided by the adjacent is tan of the angle, so tan of pi over 4 by trigonometry. So we know that the gradient is just equal to tan of the angle. So in this case, the gradient is equal to 1 because tan of pi over 4 is 1. So we know that the gradient of this line is 1, so the equation of this line, because it goes through this point with coordinate 3, 0, the equation of the line is going to be y minus 0 equals 1 x minus 3, or just y equals x minus 3. Now, if I write the Cartesian equation of this line, I've got to be careful because I know that the line only moves to the right. So I need to give the condition that this is only true when x is greater than 3. We don't want this dotted part of the line to the left of 3. And the final way that we're going to come up with the equation of this line is to say, well, one way of thinking about it is we know z is going to be some complex number. Let's say z is x plus iy. So we want to find out what coordinates x, y satisfy this condition. So let's replace z with x plus iy. And like we always do when we're solving a problem like this, we're going to simplify this complex number and we're going to collect together the real parts and the imaginary parts. So the real part is x minus 3 and the imaginary part is iy. So now we're kind of forgetting about the diagram and we've just got a problem where we've got this complex number, which I'm shading in yellow, and I know the argument of that complex number. Well, a useful fact to know is that if you do tan of a complex number's argument, so if we do tan of the argument of this yellow complex number, which we're told is pi over 4, that's what this says, that's equal to the imaginary part of this complex number, which is y, divided by the real part, which is x minus 3. If you're not happy with using that formula, just think about this yellow complex number. If we were to sketch this yellow complex number, we know that it's going to be somewhere on this line, which moves off at an angle of pi over 4. So let's put it there. And we know that the real part of this yellow complex number is x minus 3. And the imaginary part is y. And this is our complex number. X minus 3 is the real part plus iy. So we can just draw in a right angle triangle here. And we know that tan of pi over 4 is equal to the opposite side length, which is y, the imaginary part, divided by the adjacent, which is the real part. So we get that formula there. And we know that tan of pi over 4 is 1, so we know that 1 is equal to y over x minus 3. So we can rearrange this to get y equals x minus 3. And it turns out that these two ways are actually identical to each other. Because if we said, well, let's say that this coordinate is xy, and we want to know what equation does x and y satisfy, well, we know that this side length here is just going to be equal to y, and this side length here on our triangle is x minus 3. Let's label that in red. So that side length there is y, that side length there is x minus 3. So you've got exactly the same situation that you had before. Tan of pi over 4 equals y over x minus 3.